Okay, hello everyone. Welcome to Math 1510, Deep Learning Theory and Data Science. It seems last time I looked at the poll that the majority of people are interested in delaying the presentation. So it seems like they're going to be delayed. I didn't check today what is the status of the poll. Maybe I can quickly check. Let us see. Uh, let's see. Yeah, it seems like there's a majority of people who want to delay it. Okay, so in the previous lecture, we've discussed kernel methods in machine learning. And today we're going to discuss something called the neural network Gaussian process, in short, NNGP. And what we're going to do in the next lecture is we're going to show how both of these are related. Okay, so we're building our story one piece at a time, and it should become clear next time, or maybe at the end of this lecture, what is it that we're trying to understand. So let us begin by recalling an experiment that we discussed somewhere in the beginning of the lecture, of the course, sorry. And the experiment is by Neishabur, Tomioka, and Natis Rebro. And it says the following. Imagine that you train a two-layer neural network, two hidden layers, with varying width. So here's the width. Width, I remind you, is the number of rows in a fully connected layer. And imagine that you track the train and test error. And you try to understand how does it behave. So what you can observe here, the black line is the train error. And we can see that at some point it becomes very small and essentially zero, right? So this is called the point of interpolation. Interpolation of what? Interpolation of the training data, okay? Point of interpolation. Now, more importantly to us, we can see here, how do you train them for the same number of epochs and such? I believe so, I believe so. I mean, I don't remember the trainings, specifics from the paper. You can look at the paper, but I would be surprised if it's not the same number of epochs and such. And so what you can see here is the test error as function of the width. And what you can observe is that the test error keeps improving, right? Do you see? Keeps improving, keeps decreasing. And you can see how the same happens for MNIST and CIFAR10. In the case of CIFAR10, again, the test error keeps improving. Now, why is this significant? Does anyone know? What is the significance? Overparameterization and overfitting. Yeah, Nia is correct. So basically the significance is that overparameterization and overfitting are improving the test error, right? So this serves as a motivation for going beyond 4K all the way to infinity. What's the difference between 4,000 and infinity? Very little, right? And so what we're going to do is we're going to investigate the same thing for statisticians. Yeah. What we're going to do is investigate what is happening once we literally get to infinity. Okay. Now, here is a little bit of more motivation. So this paper is by, I believe it's pronounced Jae-Hoon Lee from Google Brain, I believe. In this plot, you can see on the x-axis, the width of a 5 hidden layer fully connected network. And you can see how they do experiments with ReLU and tanh nonlinearities. And on the y-axis, you can see the generalization gap, which is just a fancy way of saying test error. Okay. Now, what can you observe happens here? You can observe that it decreases with width, right? So because it is Google Brain, they have a bigger computer than you. So they go from 4K all the way to 20K. When I tried to run experiments with 20K parameters, my computer crashed. You see? So that's why you go to Google to get bigger computers. So here you can see the same phenomenon. Again, 20K gives you the best performance. Now, you might think that, this width, improvement with width maybe makes sense for a fully connected layer, but what about a convolutional layer, right? What would you do in the case of a convolutional layer? If I had to, if you were tasked to grow a convolutional network somehow to infinity, what would you do? Alex says immediately more filters. That is correct. That is correct. So indeed, that is what they did in a follow-up work by Novak et al. So what Novak et al. Show is that if you put on the x-axis the number of channels now, channels in a convolutional layer, and on the y-axis the accuracy, you can see how the accuracy improves with the number of channels, right? So in the networks that you were looking at in the homeworks, the number of channels is usually something like 64, 128, 256, maybe 512. Here they go all the way to 1,000. Why doesn't the same happen for tanh? There is no tanh here. Do you mean in the previous slide, Amareza? In the previous slide. It does happen. So when you train a bunch of networks, you need to decide on some, it's not random, it is not random. So notice that if you read carefully what they're saying generalization gap, which is fancy word for test error, for a 5 hidden layer fully connected network with various widths using ReLU and tanh nonlinearities on CIFAR10, random optimization and initialization hyperparameters were used and results were filtered for networks with 100 classification training accuracy, resulting in a total of 125 tanh and 55 ReLU networks. The best generalizing networks are consistently the widest. So the way you should interpret this, in my opinion, you can interpret it however you want, but my perspective is that all of these points here are various networks that were trained with different random initializations, and some of them perform well, some don't. Now, if you're in a company, let's say you have a startup company, Amireza Incorporated or something, and you're trying to get the best performance for your company, then you don't actually care about the networks that don't perform well, right? You just pick the best network and you don't care about anything else. So in reality, the only thing that matters is the lower envelope of the plot. And the lower envelope is improving, right? So of course, there's networks which are horrible for whatever reason that probably no one actually understands. Like, there's probably points here that are failing completely. But, under certain conditions, you get to this lower envelope, and that's performing increasingly well with increasing width. And here again, I repeat, we see the same phenomenon once we increase the number of channels, which is that width, increased width improves accuracy. Okay. Now, this idea of studying networks which have infinite width is not very, it is something that was considered in the past, in particular by Radford Neil from University of Toronto. That's where we are. And in this paper, so this is a pretty old paper. It's from it's actually not a paper, it's a technical report from 1994, where what is being discussed is essentially the same idea of growing the size of the network to infinity. I will not read the abstract, but I just want to mention that this is the, I believe this is the first reference of a person who was interested in infinite width networks. And so later in the deep learning revolution, so the first paper that came after the 2010s that again studied infinite width networks was by these people, mostly from Stanford and Google Brain. Again, I will not go into the abstract, but essentially what these people were doing was studying the features of infinite width networks. So they were looking at a fully connected infinite width network, and they were studying the activations, how they behave as function of depth. And later on, they had other follow-up papers that again looked at different properties of infinite width networks. Usually these specific researchers, when they say mean field theory of high dimensional chaos, basically that means that they're studying infinite width networks. It's like their way of saying infinite width. So here you can see infinite width, and here you can see mean field theory, infinite width, and so on. I don't want to go into details of what these works are doing, because I will soon explain what is happening for an infinite width network in my own words. Okay. Maybe we'll just read a bit from the abstract. So we studied the behavior of untrained neural networks whose weights and biases are randomly distributed using mean field theory. So again, that means infinite width. We show the existence of depth scales that naturally limit the maximum depth of signal propagation through these random networks. So essentially they're studying a network which has infinite width, and they're trying to understand what happens with the data as it propagates throughout the networks. That's what this paper is doing. Yeah, and in this lecture, what I'm going to focus is on this paper by Jae-Hoon Lee from Google Brain, Jae-Hoon Lee, Yaseman Bari, Roman Novak, Samuel Schoenholz, probably butchering that name, Jeffrey Pennington, and Jascha Sol, I don't know how to pronounce it, Dickstein. Okay. And I'll also discuss in this presentation or in this lecture their follow-up paper that discusses convolutional networks, okay? So this is kind of a short literature review in case you are interested in studying this in depth beyond what is going to be presented in the lecture. So let's get to what is exactly the benefit of looking at infinite width networks. So imagine that we have an input vector x, and imagine that we multiply this input vector x by some weight matrix, which I'm going to denote W1. Whenever I put these things, it means that it's a capital letter. The reason I have to specify that is that my handwriting is unfortunately absolutely atrocious. So it's probably unclear what is capital, what is not. Now imagine that I look at a single row from this weight matrix and I call it lowercase w1. Okay. Now we can write the output of this fully connected, layer is going to be something like x lowercase x transpose w1 plus a bias b1, right? Simple. Now imagine if we take all of our data set, all the examples, and we repeat this process. In that case, you would have a capital X multiplied by W1 plus B1, right? And I'm going to denote this by Z1. So let me try to explain what happened here. Let me try to explain what does this mean. So X is the following thing here. X is a matrix in R of size D0 times N. So it's a matrix that contains in its columns the different samples in your training data. Okay, so it would be something like X1, the first example in the data set, X2, right? Now, imagine that we multiply this X matrix by a single row from the first fully connected layer. Then this can be thought of as taking this is the first signal here. This is the first training example. Let's say X1 or something. So first training example. First training example is this, right? And so you multiply this by the weight matrix, and that gives you this circle right here, right? And then you multiply the second training example, which is this thing, and that would give you this circle right here. And you repeat this for all your sample size, all your different examples, and you get this vector here. Does this make sense? Any questions? Ask now or forever hold your, how was it? Forever hold your peace. I think that was what we learned in some lecture. You add a 1 to the end of X to account for the bias. No, I'm just going to write the bias explicitly. In this plot, there is no bias. Just so let me remove all of this annotation to gain again the original plot. So basically, this is X, and this blue shaped thing is going to be denoted by Z1. And so this thing is Z1, which is equal to X transpose W1 plus B1 vector, right? Why do we have B times the 1's vector? Because we want to use the same bias for all the examples. Now, notice that Z1 is in Rn because it's of length number of examples in your data set. A different way to describe Z1 would be take a fully connected layer, pick one of the filters in the fully connected layers, and just calculate the inner product of that filter with your whole data set. I see some confused faces, so does anyone want to maybe ask a question to clarify? Otherwise, it will be even more confusing in the future.
Wait, so on the left we have the X matrix, and then we're multiplying that by all the rows in W and getting this new matrix.
No, we're take. Oh yeah. So each one of these things would be corresponding to a different row in W. That is correct, yes. And so notice that because we're assuming an infinite width network, then the number of rows is tending to infinity, right? And so based on what Gina said, each row here corresponds to a different filter. And so the hidden layer dimension tends to infinity. Okay. So if that's clear, what we're going to do now is we're going to study a little bit what are the properties of this Z1. So here you have a reminder of all the quantities which are in place. So we have the input matrix, which is X, which is of size D0 times the sample size N. D0 is the dimension of the input. N is the number of examples in the training data. We have W1, which is a single row from the first fully connected layer. And we have a bias. And we have this calculation that we did, Z1. And Z1 is the first layer pre-activation of a single filter. That's the verbal description of it, in case you like verbal descriptions of quantities. Now, what's important is this column, which says that you should think of your input, the whole training data, as just being a fixed quantity, whereas the rest of the quantities should be thought of as being random. In particular, you should think of W1 and B1 as being random. Can anyone explain to me why should we assume that the W1 and B1 are random quantities? Why would we want that?
I guess if you're training a neural network, these would be randomly initialized.
Yes, that's part of the explanation. That is part of the explanation by Tristan. So it's correct that W1 and B1 are randomly initialized, so it makes sense to think about them as random variables. But there is an extra aspect to this, which is that the number of rows that we have is also infinite, right? So you can think of each row as being a sample from a distribution, right? By the way, some of the calculations I'm going to do in this lecture might make the mathematicians in the crowd, unhappy. Like, there's going to be infinite matrices with infinite rows and, multiplications of matrices with infinite rows. So I apologize in advance if I insult you with this lack of rigor. Please do forgive me. So what we're going to do is we're going to recall that a deep network is usually initialized with entries which are just taken from a normal distribution. So this is a multivariate normal distribution, which is in reality, it has independent entries, right? So usually the way you initialize networks is you set the entries of the weights to be zero mean and certain variance. Okay? And so here we're writing some, strange variance, which is sigma W, which is the variance of the weights divided by the input dimension, but it doesn't really matter. You can think of this as a number. Moreover, we're going to assume that the bias is initialized from a normal distribution as well. Okay. Now, notice the following interesting observation. Notice that we can, first of all, we know what is the distribution of Z1. Can anyone tell me, why do we know what is the distribution of Z1? Hint, it is something that was mentioned in the course at some point.
It's just an affine map applied to a Gaussian random variable.
Exactly. Thank you, Tristan. Yes. So if W1 is Gaussian and B is Gaussian, if you apply an affine map of them, it just stays Gaussian. So more precisely, X is fixed. And if you multiply a fixed matrix by a Gaussian, you get something which is Gaussian. And if you add an independent Gaussian, you get something which is Gaussian as well. Okay. Now, because it's a Gaussian, the next thing we might want to do is we might want to calculate its mean and variance, right? That's usually what you do with Gaussians. You estimate their parameters. So let us do that. So first we calculate the expectation, the mean. The expectation is equal to, we just plug in the definition of Z1. So we get X transpose W1 plus B1 times 1. Do you recognize this? This is basically the same formula as here. Same thing. Now, I claim that the expectation is 0. Why is it 0? Because W1, first of all, what are we taking the expectation of? It's over W1 and B1, right? And why is the expectation 0? Because by linearity of expectation. Yes, thank you. Thank you. Now, let us move to the variance. So this is the variance. So the variance of Z1, actually, it's not the variance, it's the covariance. Let us be precise. The covariance of Z1 is equal to the expectation of this quantity. So I'm just plugging instead of Z1 this thing, instead of Z1 this thing. And then if you open up the expressions, one of the expressions you would get is something like expectation of X transpose W1 transpose X. That's going to be one of the expressions, right? And for example, that expression, if you take the expectation of W1 transpose, that's simply equal to an identity, right? Times a scalar. And so that is why we obtain this quantity. And because W1 and B1 are independent, then the cross terms are 0. And if you calculate B1 times B1 transpose, you get this quantity. Okay, it's just simple linearity of expectations, as Neo has told us. Okay. So Amireza is asking, why would you assume X is constant but W1 is random? Due to your reasoning, if the number of rows is infinite, then X can be sampled from a distribution but known to us. One way to answer your question, Amireza, is if we look at experiments such as these ones, right? The data here is literally fixed. The data is like CIFAR or MNIST. It's just fixed numbers, right? The only thing that we care about is the behavior as the size of the network tends to infinity. And because of the size of the network tending to infinity, we think of the weights as being random. And because the data set is fixed, we think of it as being constant. Does that answer your question, Amireza? To a reasonable degree? No, X is not infinity by n. So if you look at this plot, this figure, notice how X is D0, which is some fixed dimension. In our case, for MNIST, it's 728, and sample size is the number of examples. For MNIST, for it's 50,000, right? So it is fixed. So Neo is asking, what is the definition of K0 and K1? So K0 is X transpose X, and K1 is just what is written here to the left. Okay. So the interpretation of K0, because it's defined to be X transpose X, you should think of it as a gram matrix, which just calculates inner products between your different data points. Forgot to improve my lighting today, 1 second. Like keeping my lighting. I was told that professional, videographers always have good lighting. I haven't purchased, do you see now my face is slightly pinker? Look now, not pink, pinker. Do you see the difference? It's not particularly important. You don't see a difference? We try again. No light. With light. Not even. I've made a purchase which is meaningless. I'm just wasting my money. Space lighting is pretty good. Okay, yeah. Space is illuminating me. So The way to think about K0 is that it's just a matrix that's calculating inner products between different examples in your data set. And notice that this is very important. No difference, that is very unfortunate. K0 is of size n by n. So n by n means it's a matrix of size number of samples in the data set times number of samples. I'm trying to increase the light in my room. So K0 is of size sample size by sample size. And K1 is also a matrix of size sample size by sample size. What is the difference between K0 and K1? Can anyone tell me? It seems like both matrices have the same dimensions. So why do we care about K0 and K1? A translation of what? Oh, it is translating, but what's in words, what is the description of K0 and K1? K0 is a gram. K1 takes into account the bias. That is correct, Jack. But what I'm trying to get at is that K0 is a gram of the training data, training images, let's say, whereas K1 is the gram of your pre-activations. So it's like one layer deeper into the network, right? Because you can see that it's, expectation of Z1 transpose, where Z1 is the pre-activations after the first fully connected layer. So what we have achieved thus far is we've calculated the distribution of the pre-activations one layer deeper into the network. Can anyone guess what will we do next? Iterate this process, exactly. Yes, that is what we're going to do. Everything you've said is in fact correct, and there will be a ReLU. So what we're going to do next is continue to the next layer. So imagine that we take a certain Z1. So Z1 was a vector in Rn, right? And imagine that we construct a big matrix, which is called Z1. Z1 is a matrix which has lowercase z1 as one of its rows. And imagine that we take a single, so let me make a small drawing here. So this would be, let's say this is X and this is W1. And we took one W1 to create Z1. And now we're looking at a different fully connected matrix W2. In between, there's of course a ReLU that we must not forget. And here we're going to take another row W2. Now notice that we can write the output of W2 as lowercase, so basically what's written here. So notice that we take Z1, and first of all, we follow Neo's suggestion and apply a ReLU on it, right? Because we take the pre-activations and we apply the activation on them. And this is applied element-wise. So on each one of these circles right here, we apply a ReLU. If it's below 0, it becomes 0. If it's above 0, it is unchanged. Then we take this matrix and we multiply it by W2, which is a single row from W2, capital. Then we add a bias multiplied by 1n, and we get another vector in Rn. Does this make sense? Does make sense? Does anyone have any questions?
So does the support of W2, is that finite or something? How do we deal with the infinite length of.
Yeah, so this is why I said this is a slightly, ever so slightly non-rigorous. So there's a question of order of limits. Basically, you can think of this as there's certain works that take limits in a certain order. There's other works that take all the limits together. We're just going to ignore it because I don't think this will be, I don't think it's a good idea to discuss such issues. But you do have a point in that W2 is a matrix now of infinity by infinity, which is a bit strange. I agree with that. I do agree with that. So as a small side note, if you look at their original paper, I don't think they addressed the issue that you're mentioning, Tristan. So I think they're just kind of like ignoring it. But in follow-up papers, I think they have more rigorous calculations. But I will not discuss them. So again, just to reiterate, we have X, we apply W1, we got Z1. Now we construct a matrix capital Z1, and we take capital Z1, apply a ReLU on it, multiply by a row from W2, and then we get Z2 after we add the bias. Does anyone else have any questions? No questions? Okay, so let us look at the equations here. So what we have now is Z1 are the first layer pre-activations. And so those are a matrix of size D1 times N. N is the sample size and D1 is the dimension of the first hidden layer. So Z1 is this matrix, right? So it's dimension D1 growing to infinity times N. And so Z1 is a matrix with infinite rows. Let's put the quotation marks not to enrage anyone in the crowd. And then what we have is W2, which is a row from the second layer weight matrix, and B2, which is the bias corresponding to W2, and Z2, which is what happens after we multiply Z1, the value of Z1 by W2 and B2 according to this equation. And again, I want to reiterate that we think of W2 as being random, we think of B2 as being random, we think of Z2 as being random. Okay. So all of these are random quantities. Why do we think of W2 as being random? Because again, W2 is initialized from a random distribution, because that's how networks are initialized in practice. And we have essentially infinite rows in capital W2. So you can think of each row as being a sample from a distribution. Now, at this point, notice the following thing. Let us cross this out. Hopefully no one saw what was written. So the question is, why would Z2 be distributed as a normal? Why? You see that the title of this lecture presentation was Gaussian neural network Gaussian process. So it seems like everything is going to be Gaussian today, right? So Neo shows skepticism towards the idea that Z2 is a normal, saying that Z2 is related to some ReLU, and that makes him skeptical about its Gaussianity. Does anyone have, so Amireza is skeptical as well. Like you did way back, says Justin. What did we do way back? So way back, the reason why we had a Gaussian distribution the reason why Z1 was Gaussian was because this was constant, right? And W1 was random. And so if you multiply a constant by a random, you get a random distribution. But if now we have, instead of a constant, we have some Z1, which is somewhat of a random matrix, right? Z1 is actually a random matrix. Its entries are random, so it becomes a bit strange. You see, we don't, like Z1 is an infinite matrix with random entries. So you don't actually know, it's not constant. Does that make sense, Justin? Yeah. So does anyone else have any thoughts? What could we possibly do? So let me ask you this. I assume everyone learned, so probability is not a prerequisite for the course, but I guess some people took probability. Where do normal distributions arise in probability? In which context? Everywhere. That is correct, central limit stuff. And this is exactly the reason why this is random, just central limit theorem. So the idea is the following. Notice that W2 is a vector which is in RD1, right? Now D1 is tending to infinity. So it's kind of like an infinite vector. Now notice that sigma Z1 would be something like this, right? So this would be W2, which is of size infinity. And here you would have sigma Z1 transpose, right? And so when you multiply this row by this column, you have essentially a sum over infinite quantities, right? And so if you have a sum over infinite quantities, it's sum of infinite random quantities by the central limit theorem, it converges to being a Gaussian. Let me quote to you the central limit theorem. I have it in front of me. So it says the following. In probability theory, the central limit theorem establishes that in many situations, when independent random variables are added, then their sum tends towards a normal distribution, even if the original variables themselves are not normally distributed. Amazing theorem, let's say, amazing. So basically the fact that the dimension tends to infinity implies that we're summing infinite random quantities, which implies that we probably have something like a Gaussian distributed variable. Amireza seems unpleased. If the nonlinearity was two-sided, like tan H, it would make more sense to consider Z2 as a Gaussian. But ReLU is one-sided and it cuts out, and it's not obvious to me how you deal with this type of nonlinearity. One-sided cuts out, not obvious. Oh, you agree now? Okay. So Neo is saying, I see, so the infinite dimensionality gets rid of the ReLU problem. Exactly. Don't you have to appropriately normalize the distributions though? You do. That is a beautiful question, Neo. And that is why we're assuming that the variance here is sigma W squared. So think of sigma W squared as like 5 or pi. I assume that's your favorite number, pi. And divided by D1. So once you divide by D1, it makes it so that the integral or the sum would be dividing by the number of contributions. Stephen is asking, I think it might not be standard Gaussian. You might have to recenter it. Yeah. So what we're going to do is we're going to calculate the expectation and the covariance of Z2, and then we will see whether it is standard or not standard. That is correct, Stephen. Okay, so we can proceed. So hopefully you are somewhat convinced. By the way, one thing that I should mention is that the central limit theorem does have assumptions, right? So one assumption in the central limit theorem is that the variance has to be bounded, cannot be infinity, right? So you could question whether the variance here is finite. That's one way to question. But you're applying a ReLU on them, right? So if you have a I guess it should be. I guess it should be bounded. Anyway, so what we're going to do next is we're going to look at the expectation and the covariance. So the expectation of Z2 is equal to the expectation over W2 and B2 of sigma Z1 transpose W2 plus B2 And so because of, again, linearity of expectation, you get that this thing is equal to 0. So that means that Z2 has 0 mean. And then we calculate the covariance. And so, again, it's just similar calculations. You just plug instead of Z2, this equation, use just simple algebra, hope that you're not breaking laws of basic logic by using infinite width and height matrices, and you end up with this beautiful expression. By letting D1 tend to infinity, are we considering the limiting distribution of normal distribution with decreasing variance? Yes, that is correct, Jack. That is correct. That is correct. Is it obvious that the covariance matrix is bounded when the dimension is infinity? But nothing is obvious about what is happening here. By the way, you shouldn't blame me for the lack of mathematical rigorness. I'm the messenger. That they say, what do they say? Don't shoot the messenger. Don't hate the player, hate the game, something like that. I'm just presenting to you what is happening in the arena of deep learning, right? Medium is the message, so you do want to shoot me. That is unfortunate. Yeah, that is unfortunate. Yeah, so it is slightly non-rigorous what is happening here. Yeah, but I think it's important to show this topic because it's quite popular in the arena. So I think it's definitely worth seeing it, despite the lack of rigor. Okay, so what's happening next is just you calculate these expectations and you get this quantity, which makes a lot of sense. So notice what's happening here is kind of interesting. So notice that what's happening here is if you look at the expectation of sigma Z1 W2, run out of space, and then W2 transpose times sigma Z1, right? And then you can write it. So first of all, if you do the expectation, then the W2 transpose becomes an identity times a scalar, right? And so what you're left with is basically sigma Z1 transpose. But because Z1 is a matrix, then you can write this matrix multiplication as a sum over the columns, lowercase z1 transpose with a sigma, right? So basically here we had, here in this equation, it's capital Z, so it's a matrix, right? It's a matrix. But what happens here is that we're writing the matrix multiplied by the matrix transpose as a sum over an outer product. So now it becomes a vector. Now, why do we have here an expectation over Z1? Does anyone know? While you think, I can write this a bit more clearly. Again, my handwriting is absolutely atrocious. So if you have expectation of Z1, sigma Z1 transpose. Yeah, so the question is, why is there this expectation here? If anyone knows, why is there an expectation? Yeah, exactly. So essentially, let me try and maybe draw it. No room for writing an equation, unfortunately. So if this is Z1, sigma Z1, and this is sigma Z1 transpose, then here there is a bunch of columns, right? And a bunch of rows. And you know that if you do matrix-matrix multiplication, you can write it as a sum of outer products, right? Of the columns and rows. Now, notice that we have infinite columns and infinite rows. So infinite columns in Z1 and infinite rows in Z1 transpose. And so this sum essentially becomes an integral. If you're summing over infinite replications of variables coming from a distribution, it becomes an integral and essentially an expectation over Z1 coming from this distribution. I feel like Tristan likes this transition. Tristan is impressed. Or maybe it's the phase that why are we doing transitioning from infinite sums to expectations in such a bizarre manner? So notice that the nice thing here is that Z1, right, is distributed as a normal with 0 K1. So notice this K1 is what we've previously calculated, because in the previous slide, we showed that Z1 is, let's highlight the most important thing here. Z1 is normal 0 K1, right? So we know the distribution of Z1, it's multivariate normal with a covariance K1. And so what we're doing here is we're using this knowledge. So we're sampling a bunch of Z1s from this distribution and we're calculating their outer product. And again, the reason is because if you're multiplying, me right here, a proper explanation. So if you have an expectation, or if you have a sigma Z, capital Z1, sigma capital Z1 transpose, it's equal to sum over I, let's say, and then you have smaller case Zi, Z1 I, let's call it Z1. So now it's lowercase, there's no Z1 I transpose, right? This is just multiplication of matrices can be written as sum of outer products of columns and rows. And then this thing is kind of like an expectation over Z1 transpose, where Z1 is distributed according to a normal distribution. Does this make more sense now? Or is this still bizarre? Bizarre. Is there part of this which is not clear? Amireza is asking, is it possible to calculate or approximate this expectation analytically? Yes. I'll comment on this in the future sometime. It is possible, yeah. So does anyone want to ask any questions? I guess the biggest thing that might be unclear here, I don't know what's unclear, but the biggest thing is, why is this correct? This is correct because you're summing, if you're summing a bunch of Z1s, right, which are just copies coming from a certain distribution, and I goes from 1 to infinity, then it's basically converging to the expectation of Z1 transpose. A sum becomes an expectation if you have infinite elements in the sum.
But shouldn't we need some like weighting to make this thing not blow up?
Yeah, so there is weighting in the Z's, right? So the Z's have a weighting that prevents them from blowing up. If you look like very carefully in these calculations, you would see it doesn't blow up. In fact, I can show you exactly where it is. So notice that, okay, so when you, okay, let me add another step. So the step before this was expectation over sigma Z1, so this is capital Z1, times W2 transpose sigma Z1, right? Now, if you remember, we said that the expectation of W2 transpose is an identity multiplied by a scalar. Now, the scalar is the scalar that's written here. So it's 1 over D1, and that's literally the one that you would need in order for this sum to be non-blowing up. I guess I should write here something like this, or maybe it would be better if I write something like 1 over D, 0 or something like that. So there's some constant, maybe it's D0, maybe it's D1. I hope I didn't get it incorrect, but you can see the answer. Jack is asking, should the expectation be an integral? My expectations are always integral, so I'm not sure I understand the question. Yeah, so it's an integral. When I write expectation, I mean integral over the quantity multiplied by probability. I'm not sure I understand. It is an integral, but maybe you're thinking about a different definition of expectation that I'm not quite understanding. So if there's one thing that you should take away from this slide, is that at the end of the day, what we've managed to claim was that Z2 has an expectation 0 and a covariance which is equal to this quantity. And what we're going to do is call this K2. So let me just show you a clean summary of what is being claimed. A clean summary. You see, this is why you need slides in courses, because otherwise it's very hard to create clean summary. So we take X, which is a matrix of our data. X is a matrix which contains X1, X2, and so on, right? Cats, dogs, frogs, etc. We construct a gram, which is of size n by n, sample size by sample size, matrix of inner products of every 2 examples. Why do I do this motion? Because it's like an inner product of a sample coming from here and here. They meet, calculate dot product, right? So K1 is K0, sorry, is a matrix of inner products of your training data points. And then we calculated K1. K1 was equal to K0 multiplied by a scalar plus a bias times 1, transpose. So this is the gram of the pre-activations, gram of pre-activations. And then the beautiful thing happens, which is we take K1 and we calculate using K1 an expectation over Z1, where Z1 is distributed normal K1. So let me highlight this so it's super clear. So this is K1, right? And we know that Z1 is distributed normal as 0K1. And then what we do is we sample here Z1s from this normal 0K1, and we calculate the expectation of sigma Z1 transpose. And then again, we have multiplication by some variance plus bias 1, transpose. So let me ask you a question. Right, and notice that here there is a sigma W and a sigma B because that's corresponding to the next fully connected layer. And then you can just iterate this as many times as you want. Does anyone have any questions about this? Any questions? So the idea is that you can calculate the distributions of all deactivations, pre-activations in the network because everything is just Gaussian. And I should emphasize that all of this is done at initialization, at initialization, at initialization. I repeat at initialization several times just to emphasize that this is not at training, it's at initialization. Training will come in the next topic, in this next lecture. So Amireza is asking, is the number of layers finite? In what we're currently discussing, it is finite, but there are works by some of these authors which analyze what happens if you have infinite number of layers as well. One thing that these authors do, for example, is because they know the distribution of the activations in each layer, they can analyze how does the distribution behave after many, many layers, right? And you can study that and you can show that there's some interesting phenomena that happen, something called the edge of chaos. It is even more weird to have infinite layers. How does infinite layers work? Yes, so I'm not going to discuss the infinite layers in the lecture. Not going to discuss it. But basically in infinite layers, you would have, you would just create like K as function of L plus 1. You write it as a function of K at layer L, right, based on these equations. And then you just study what happens as L tends to infinity. And you get that there is some type of an interesting behavior that emerges. But again, I won't go into that. Now, at this point, you see some convergence will emerge. Not always. So actually it depends on how do you choose the variance of the weights and biases. Depending on how you choose the variance of the weights and biases, you might get different behaviors. So if anyone's interested in studying this, look for the edge of chaos. Edge of chaos. Beautiful name. Edge of chaos. There's a paper and it studies this equation in detail. Okay, so at this point, you might ask yourself, what happens if we have a convolutional layer instead of a fully connected layer? So in a case of a convolutional layer, what happens is that instead of having an equation, for example, Z1 is equal to X transpose W1 plus B1. Do you remember this equation appeared a few slides ago? Instead of having this equation, you would have an equation that says Z1 is equal to P of X transpose W1 plus B1, where P of X is now a matrix that instead of containing the different examples in its columns, it contains patches of the size of the convolutional layer, like 3 by 3 patches from the input data. So it's basically a matrix that instead of having, X, which contains in each column a different example, you would have patches of X, which would contain patches from the first image, patches from the second image, and so on. I think that I will not go too much into it. Let me just go briefly and show you how does this look. So basically the equation looks the same, except instead of looking at the X matrix of the different training examples, you look now at the patches, what is the intuition, by the way, behind looking at the patches? If you have a, let's say, an input image, right, and you convolve it with a filter, then you're essentially placing here a certain filter, and you're calculating a dot product of this filter with that neighborhood in the image, and that creates a certain scalar, right? And so essentially this scalar is what's called Z1 here, right? So you essentially multiply the filter W1 times different patches in the images, and that gives you this scalar here. And you can repeat the same steps that we previously did and show that the expectation of this Z1 is equal to 0, and the variance is equal to, the covariance, sorry, of this Z1 is equal to some gram matrix of the patches. I guess it's not easy to see that. The second convolutional layer was supposed to be homework. Unfortunately, these were, what's the word? These were eliminated from the course. There are no problem sets. Okay, so let us discuss, yeah, that would have been not true. Let us discuss a little bit of more measurements. So in this figure by Jae-Hoon Lee, what they're doing is they're comparing the performance of several networks. Wow, technology, look at it. So here what you can see is NN stands for neural network. W5 stands for width of 5. NNW10 stands for a neural network with width 10. What you can see is that the width is increasing all the way to 5,000, right? And you can see that the plots which have this, how do you call it, a dotted pattern, the discontinuous curves are the neural network. The blue curve, the discontinuous blue curve, is the best neural network, and the infinite width NNGP is the black curve. So the black curve is what happens if you calculate analytically the prediction of the network. So basically, if your network is of infinite width, you can calculate what is the network going to predict once the number of weights tends to infinity. What happened here? Okay. So essentially what we've seen is that you can predict it should be the max of the other curves. So what we've seen is that you can predict how do the different features behave, and based on these calculations, you can predict, you can use these calculations to predict the, to calculate the predictions of the infinite network on a test point. And so that's what they're doing. And the point of this is that they're interested in comparing how well does an infinite width network behave compared to a finite neural network, right? And so what you can see and what they want you to see is that for the most part, in the case of accuracy, you can see that in some cases, like CIFAR value, it seems like their infinite width network is performing better than deep networks. But in other cases, like MNIST-ReLU, it seems like they're performing the same. Yes. I'm not sure, by the way, why is this blue curve not above all other curves? That's kind of strange, I must say. There's something strange about how they're picking this curve, but it doesn't matter for the main point. Yeah, I'm not sure what's, maybe they picked like the best Better on average, yeah, maybe. Not sure, not sure. Let's see the caption. Does the caption illuminate? So NNGP outperforms finite width networks. Neural network performance more closely resembles NNGP increasing width. Best performing on validation set neural network across all widths and trials. So they probably use the validation set, right? So because you have a validation set, it implies that you're picking the best network. Doesn't matter really. I think it's because they have trained, they have validation, and they have test. I think that's why, but doesn't really matter. The main point is that increasing width seems to increase performance, and it seems like in some cases their infinite width network is performing better. Amireza is asking, did they consider the same number of layers for different settings in this experiment? I believe it is the same number of layers. I do believe that. I do believe that. Okay. Okay. So here's another interesting result that they have. So in this plot is from the paper by Novak et al., where they were looking at infinite width, infinite wide networks. And they started by looking at the performance of fully connected networks. So this is fully connected networks in blue versus the Gaussian process, infinite width networks. So you can see that for fully connected networks, you get better performance by using their infinite width networks, right? 54% versus 59%. And what they did was they checked what happens if instead of using a fully connected layer, you use local connectivity. What does local connectivity mean? Local connectivity is like a convolutional layer, but you don't share the weights of the different shifts. So you reduce the size of the weights to a fixed limited spatial size, like 3 by 3, but the weights in different locations of the images are not the same, not the same. And what you can see here is that they're comparing the network. In blue is the regular training networks, and in red, it's their infinite width networks. And you can see they perform basically the same. And then the next important thing is what happens if you do weight sharing, local weight sharing, which they call equivariance, which is basically a convolutional neural network. And what they show is that a neural network is able to increase performance by a lot, whereas an infinite width networks is not able to improve performance. Was there a question? No question. So this shows that if you train finite width networks with gradient SGD, it seems like they get a lot of performance boost due to the weight sharing, but their infinite width networks are not getting performance boost due to weight sharing. And the final plot is the performance if you also add pooling, average pooling. And so if you incorporate average pooling, then you get the accuracy of 77 for infinite width networks and 83 for finite width networks trained with SGD. Is there any satisfying explanation for this behavior of neural network Gaussian process in CNN? Not that I'm aware, but maybe in their paper they shed some light on it. Not that I'm aware. I think they do mention in the paper that they that adding the weight sharing does not affect the calculations of the covariances of the features in the different layers. But beyond that, I'm not sure. So I should really stress one thing, which is that the infinite width networks here are not being trained. Is that clear? There's no training involved in the infinite width networks, because it's kind of like you just calculate these equations right here. You just do this calculation in some way. Like you can either use something like Monte Carlo, or you can analytically calculate it. And you just get these, kernel matrices, and you use them to do the predictions. So it means that there's no training whatsoever. It's just calculations of some integrals. Whereas in the case of the real networks in blue, there's actually training with SGD, right?
So how do you use the kernels to make the
prediction? Yeah, so basically in order to do that, it's the same way that we did predictions in the previous lectures on kernels. So if you go to the previous lectures on kernels, which was called Introduction to Kernels, there should be a slide that explains this. Is there a slide? Right, so if you look at this slide, let me just remove all of these markups. Delete. So if you look at this phi x0, this slide explains how do you do the prediction. So in this slide, imagine that phi x transpose phi x is a gram matrix. So you should interpret this as some k, a gram matrix k. And y here was the labels, and phi x0 transpose phi x is the inner product between your test and trained data. So basically you just use this equation, and in this equation you use k, which is the inner product of features, and you use an inner product between your test and trained data. Does this make sense? So for example, maybe we should do a simple example. In the first layer, your data would be x transpose x you would have here, and phi x0 phi x would be x0 transpose capital X, right? And that would give you the prediction of the first layer. Then you would use that as input to the second layer, and so forth. I guess in reality, all you have to do, I believe in reality, all you have to do is actually just use the last layer, all the layers. There's also a lot of nuances to how different people do the calculations, because there's different papers on this, right? But basically it all boils down to this equation. And I believe I will explain more in detail how is this prediction being done in the next lecture. So hopefully this answered a bit the question. So I actually don't want to go into how to do the prediction, because in the next lecture, I'll actually explain this very, very clearly, very clearly. Jack, the answer to your question is yes, but you will see that in the next lecture. So this measurement shows, what's important to get from this lecture is not how to do the predictions. That's besides the point. What's important to get from this lecture is this slide. If you understand slide number 14, then that's the most important thing. The details of how to make the predictions are less interesting, because they're less important for what's to come. Okay, so this is another measurement that is trying to explore why is there a difference once we're looking at CNN without pooling? Like, why is there a difference in performance? So what they did here was they compared the, so here you can see on the x-axis the performance of the CNN without pooling, and on the y-axis you have the performance of the infinite width network. And the diagonal line means that they're performing the same. And you see there's a bunch of different networks here, and most of the in most of the cases the infinite width Gaussian process is performing better, but in some of the networks the CNN is performing the best. So this implies that the difference in performance between the infinite width network and the finite width networks is caused by a small fraction of examples of networks, which are in some sense extreme cases. So to summarize what we've seen today, we've seen that deep net performance improves with width. So that's something we've discussed also in previous lectures. We've seen that at initialization, I think I've said at initialization 8 times at this point, infinite width deep nets are Gaussian processes. We've seen that you can calculate their covariances recursively. And the question is, of course, what happens with training, right? That is the question. And I owe an explanation of how to do the predictions properly. And I will show in the next slides how to do the predictions properly. So that should be more satisfactory than my answer thus far. Okay, so we move to the next topic. The next topic is called infinite width deep nets ... neural tangent kernel. What is the neural tangent kernel, which is abbreviated as NTK? So the idea is as follows. There was a paper by Arthur Jacob, Frank Gabriel, and Clement Hongler, which is called Neural Tangent Kernel, Convergence and Generalization in Neural Networks. Let us read some part of its abstract. Hopefully, you will understand some of the words that are being used there. So they say, at initialization, you see, even they're trying to convey to you that this is at initialization. Artificial neural, this is the 9th time I think we said it. Artificial neural networks are equivalent to Gaussian process in the infinite width limit. So at the very least, you can understand the first sentence very clearly now, right? You see, they're referring what we were just discussing, thus connecting them to kernel methods, right? So because the layers have a Gaussian distribution, you can show that it's connected to a kernel method based on this equation that I showed when Tristan asked his question. So we prove that the evolution, you see the word evolution is important, of an artificial neural network during training, not at initialization, during training, can also be described by a kernel during gradient descent on the parameters of an artificial neural network. The network function f theta, which maps input vectors to output vectors or logits, follows the kernel gradient of the functional cost, which is convex in contrast to the parameters cost with respect to a new kernel, the neural tangent kernel. I will not read the rest. So basically what they're talking about here is the evolution of the network during training in the setting of infinite width networks. Okay. So I think I will skip this. So the idea is as follows. Imagine we look at the loss of a network. The loss is a sum over all examples of the loss of fxj theta, which are the logits of the jth example in the training data set, using the parameters theta, vector of all parameters, with the label yj. Think of yj as being a one hot, xj is a picture of a cat. Theta is a vector of parameters. Imagine that we look at gradient flow of parameters instead of gradient descent. What is gradient flow? Gradient flow is just a differential equation which goes into the minus gradient direction at all times. You can think of it as gradient descent as you take the step size to 0. Now notice that using chain rule, the derivative of the loss with respect to the parameters, the derivative of the loss with respect to the parameters, dl to d theta, which is equal to the gradient, is equal to the derivative of the logits with respect to the parameters times the derivative of the loss with respect to f. Chain rule, right? You remember chain rule? You like chain rule? You do. Okay, so that's what we're going to do. So instead of this derivative of the loss, we're going to write the derivative of the logits with respect to theta times the derivative of the loss with respect to the logits evaluated at the logits. Now notice the dimensions. The dimensions are extremely important here. Otherwise, if you don't pay attention to dimensions, you might get lost. So the derivative of the logits with respect to theta transpose is a P by C matrix. What is P? P is the number of parameters, and C is the number of classes. Okay. And by convention, if there is no transpose, df to d theta is going to be C by P, but because of the transpose, it's P by C. Okay. The derivative of the loss with respect to Z is simply a C by 1 vector. It's the derivative of the loss with respect to the logits. Now, imagine that we track the dynamics of the logits of the ith example as induced by the gradient flow on the parameters. So basically, the gradient flow on the parameters is changing the parameters of the model, but as you change the parameters of the model, your logits are changing, right? So the logits have a certain derivative with respect to time. Let us calculate that derivative. So the derivative of the logits with respect to time is equal to the derivative of the logits with respect to theta times the derivative of theta with respect to time. Does anyone recognize what is this maneuver? What is this sophisticated maneuver here? Do you recognize it? Have you seen it? The chain rule, exactly. Chain rule is the answer to most questions in deep learning courses. Now, at this point, what we're going to do is we'll just plug the derivative of the parameters with respect to time based on the previous equation. So if you plug the previous equation, or rather this equation, right? So the derivative of the parameters with respect to time is minus the gradient. So if you plug instead of this, minus the gradients, you get this equation, right? Now, at this point, we're going to, again, use the above equation. So we're just going to use this instead of the gradient. And that is why we get this sum over j, df to d theta, d loss to dz. Make sense? So far, just using simple dynamics of different things. Now, I'm going to copy this equation to the next slide. So again, df to dt, dynamics of the logits of the ith example xi are equal to this thing from the previous slide. Again, let us make sure that we understand the dimensions. Dimensions are the most important thing to keep track of in life. So here you can see the derivative of the loss with respect to the logits, which is a c-dimensional vector. And you can see that the derivative of f with respect to theta, which is a c by, what is t? T is time. So you should think of t as corresponding to the either epoch or SGD step. Does that make sense? So t, in SGD you have like the first step, the second step, and so on. But as you have a continuum, a continual gradient flow, instead of having discrete time steps, you have a time variable, which is continuous. Why is it not showing on the right? Because I'm trying to create compact equations. And if I would put as function of t on everything, it would prevent me from having compact equations. So if I were precise, I would have to write theta as function of t everywhere, because theta are the parameters that depend on time. It's just that writing as function of t on everything would be just make the equations unappealing. I guess they are unappealing at this point as well, but even less appealing, right? So notice that here we have the derivative of f with respect to theta, which is a c by p matrix, because f is c-dimensional, theta is p-dimensional. And here we have df to d theta transpose, which is p by c. Now, at this point, what we're going to do is we're just going to rewrite these multiplications in matrix form. So just dl to dz, you have here a bunch of different examples j, so you can just stack them on top of each other. And df xj theta to d theta, because you have different j's, you can stack them on top of each other, right? So basically, instead of writing sum of, ai bi, you can over I, you can just write it as some, something transpose something. Make sense? Now, at this point, again, let us make sure we understand the dimensions. So df to d theta is for a single example. So it's a matrix of size c times p. And we're stacking a bunch of matrices. So it's kind of like a block matrix. Now, what we're going to do is we're going to look at the dynamics instead of a single example of all the logits of the whole data set. Dynamics of all the logits of the whole data set. So now we are going to stack all the fx theta dt on top of each other, right? So now we have d to dt of the logits of the first example, second example, all the way to the last example. So this is a very long vector. Let us do a pop quiz. Does anyone know what is the dimension of this quantity? What is this? Is this a vector? Is this a tensor? Is this a 5-dimensional tensor, 4-dimensional tensor, 10-dimensional tensor? Is this not a tensor? Is this a measure maybe? Have we switched to measures? N times C is the correct answer. But when you say N times C, it's N times C vector, right? It's not N times C matrix. It's a vector of length N times C. Because each F is a vector and they're being stacked on top of each other, right? Okay, so if we're interested in this derivative, then what we have to do is simply notice that if this is xi, then I only appears here. So if you're going to stack all of this on top of each other, instead of having this thing, you will just get a stack of these things. So let me highlight this. So this is the xi, right? So you just stack them on top of each other. So this would be fx1 dfx1 theta d theta. Just stack equations on top of each other. Very, very simple. So at this point, we are ready to define what is the neural tangent kernel. The neural tangent kernel is a matrix that is defined to be this thing. This is the neural tangent kernel. Why? Here you can see neural tangent kernel, right? Now, this matrix, what is its dimension? So with the help of Neo and Juhan, we know that this is a square matrix of size Cn by Cn, right? Let us verify that we understand the dimensions here. What are the dimensions of this matrix? It would be something like, let's actually do the dimensions. What are the dimensions of this whole matrix? Does anyone know? What are the dimensions? This is an important dimension to understand. Cn by P. Wow. Wow. It is indeed Cn by P. That is correct. Now, why is this very important? Because the neural tangent kernel, first of all, it contains 3 words, right? We should discuss the name. The name is actually quite brilliant. The first word is neural. Why does it contain the word neural? Because everything in deep learning is neural, right? So you must have the word neural in the title, like neural collapse or neural networks or neural tangent kernel. So that one is obvious, right? Why do they have the word tangent? What is tangent about what we're doing? Yeah, so the gradient, basically you're calculating a derivative, so that evokes the image of something being tangent, right? We'll actually make it clearer what is tangent in probably the next lecture. But basically the fact that you're looking at gradients imply that something here is being tangent to something else, right? The derivative of the logits with respect to the parameters invokes an image in your mind of tangents. Does it invoke? Or is it does, okay. And the third word, and the most important word, the kernel, neural tangent kernel. Why does the word kernel appear in the name? Because it's a Gram matrix, inner product. That is precisely correct. And this is exactly the thing that you should remember. The neural tangent kernel is a Gram matrix. The question is a gram of what? What is being inner producted here? The thing that's being inner producted here are derivatives of logits with respect to the parameters of the model, right? So first of all, let me tidy up the equation and let's write it very compactly. Notice that if we choose the loss that we like the most, what is your favorite loss? There is only one answer to that question. Please, yes, that is correct. Yes, MSE loss, no, Neo, that is not correct. Our favorite loss is in fact not cross entropy, it is MSE. Because MSE is so nice and so pleasant, right? So why is it pleasant? Because if you look at the derivative of the loss with respect to Z, this quantity, for the MSE loss, the derivative of the loss with respect to Z is just equal to the difference between Z and the label, right? So it's basically equal to fx1 theta minus y1 for the MSE loss, right? And so this is a very simple quantity. It's just the difference between the prediction and the label. Now, notice that if we are to stack a bunch of these quantities, what we would get is fx theta minus a long vector y. So fx theta are the predictions, the logits of the whole data set concatenated on top of each other, and y are the corresponding targets, right? So by considering the mean squared error loss, we've managed to reduce this ugly expression into just fx theta minus y. Moreover, notice that this whole thing can be written as the derivative of fx theta with respect to theta. It's a bit confusing to think about it, but basically fx theta is the logits, are the logits of all the data sets stacked on top of each other. So it would be a vector of length n times c. And theta are the parameters of the model of length p. And so what's happening here is we're calculating a gram between these two quantities, and we shall denote this gram by theta xx. Why are we using a notation theta xx? Does anyone see here, why would we use such a notation? Does this remind you of anything? Kappa, exactly. That is exactly kappa. Kappa from the kernel's lecture, right? And so let me conclude by just making sure we understand what is NTK. So here's just to make sure we understand each other. So theta is a kernel. A kernel is supposed to be able to calculate inner products. Inner products between what? Inner products between, so a kernel takes as input xi and xj, which are two examples, and it's calculating the inner product between dfxi theta to d theta, logit derivative, inner product with the same thing, but with j, you see, xi, xj. Now, the thing that's a bit confusing about this definition of a kernel is that it's giving you a matrix of size c by c instead of a scalar, right? It gives you a positive semi-definite matrix. So it's kind of a generalization of a kernel, but it's okay. We know tensor analysis. We're not afraid of many dimensions. Are we? We're not. We're not. Gina is no. Okay. So notice that this is for xi and xj. Now, what you could do is ask yourself what happens is if instead of looking at a single example here, we had capital X, which is the whole data set. In that case, you just stack on top of each other replications of this. Basically, here you would take the theta of xi and x1, and here you would have theta of xi. My comma looks horrible, and x capital N, right? So just stacking together C by C matrices. And the last definition, just to make sure, theta of capital X is just a bunch of block matrices, C by C matrices, where what's important to notice is x1, 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 xn, xn, x1, xn, xn. This is the end of the lecture. Thank you for joining, and I remain for questions. Very abrupt ending. But I feel like I'm going over time. So just make sure you understand the definition of the NTK. That's important definition. And maybe a proper thing, you know, if you were to define it a bit more properly, I would define it as a matrix which has a multi-index. So I would define it as ij, maybe cc prime or something like that. Because every C by C matrix can be indexed by a C and C prime, and there's, you know, combinations of I and J. So it makes sense to think about it as 4 indices, but I'm not going to do that because the original paper did not do it. So I'm trying to make it more consistent with the original paper. Yes, Neil?
I have 2 small questions.
Mm-hmm.
The first one is, how is this like infinite, like this just infinite matrix thing? How is it connected to, how is it same or different from the case where you take the particle limit, for example?
You mean the work by Francis Bach?
Yes.
So that will be explained in, hopefully if we don't run out of time. So this should be explained in the next lecture.
Oh, I see.
But I can answer it. I don't want to spoil it too much. This is a surprise. But let me say to you this, that these works that we're discussing are talking about infinite width networks. The work that you're looking in your project is also talking about infinite width networks, right?
Right.
And there's a small but very subtle difference between the two in the assumptions that are being made. And it's related to a slide that I skipped, but I don't want to go into it. So basically there is definitely a relationship. And what we will see is that the work you're reviewing is operating in a different regime than what's happening in the neural tangent kernel. I guess these words make no sense at this point, though. So just wait for, I guess, next Monday, and then it should be clear. Does anyone know if there is a lecture this Thursday because of Easter?
I think so.
Oh, there is. Okay.
Friday is the one that is being trained.
Okay.
What?
Yeah.
Oh, sorry, you were about to say.
No, I was just going to go on a tangent related to Easter. Go ahead, please.
It's a neural tangent.
Yeah.
Okay. I have a quick question about like training a 2-layer network. So I was doing the thing I was doing yesterday, and it worked for 1 layer really, really well. So I could have these kind of mazes, and then the neural network somehow find its way to do the job. But then I tried to do it for 2 layers. So all I did was add in a fully connected layer, and then I just add in I just throw in a bunch of more parameters, apply a ReLU activation, and the 2-layer one seems to be doing worse than a 1 layer. And I'm not sure if I'm become concerned, because I would expect that the 2-layer would do better than the first 1 layer, because you have more layers and you have more more room to optimize. But I'm worried that my training method is not well, like maybe I have to adjust the learning rate.
Yeah, definitely.
Yeah, so even after adjusting should I make should I make the learning rate smaller and bigger, or do I just
play around with it? Yeah, there's no, I think usually you increase the learning rate as much as you can without it diverging. That's one way to do it.
Yeah, so
just play around with it, I guess.
So what's something reasonable to expect in a sense of 2 layers? I was having quite high expectation on the 2 layers. Namely, I was saying that, in 1 layer you have weird edges going all over the place and stuff. I was hoping that in 2 layer it can just be much, but I guess maybe you shouldn't expect that, because if you have data that are separated, if it has a weird offshoots right here that doesn't touch anything, then it shouldn't affect the loss. So there's no reason why you should expect the model to optimize. But in general, I'm hoping that the 2-layer would do better than the 1 layer. But even playing around, it doesn't seem to be doing so. And I guess the main question is, I don't know how to sort of control the experiment in a good way, so that way whatever thing you conclude from is not from like the compound of not training properly or
yeah,
so
that's the issue with deep learning. It's like, am I seeing a phenomenon that's real, or it's due to optimization issues, or like what's going on?
Yeah, so that's really what confuses me.
And there's no solution to that. If you look at the papers that the figures that I was mentioning, then they were looking at, like, the usual practice is you run a bunch of experiments over different learning rates, different initializations, and so on. Just run like a bunch of experiments, and then you pick the network that's performing best on test data, like on data that you did not use during training. And then you study that network. Does that make sense?
So train a bunch, and then pick the one.
Yeah.
Pick the most accurate one on test data.
I'm not sure I would. Yeah. So, I mean, for example, that's usually how people approach it. Is you train a bunch of networks, and then you pick the one that's performing the best on test data, and then you try to study that one.
I see.
In your case, it would mean just tune the learning rate to achieve the best test performance. And then
it would be like, because the testing data set wouldn't be too different from.
Yeah.
Oh, actually, I could generate testing because what I did was I did those bumps, and then every time it's Gaussian at these points. I could also make it uniform, but I think Gaussian makes more sense. I like Gaussian better. But
make
then
it T or something, T distribution, you know.
So maybe when you like generate testing data, you would just generate like same data structure, like the same class for each bunch, but then just generate other new points and then see how it works. So new noise, but then the same kind of underlying.
Yeah, you could do
mechanism.
that. Yeah, or you could just decrease the sample size, like train on less data, and then the task becomes significantly harder.
Sorry?
You could also
my internet just cut out.
Oh, you could also train on less data, and then the task becomes harder. Like less training data.
So less class training data, and then test it on a bigger data set. Okay, sounds good. Yeah, I think the synthetic data is good because it's simple and it's visualizable, and you can generate however many you want.
Yeah, definitely. And do you see any interesting phenomena? Like in the original, the paper that you were looking at, or I guess the follow-up paper, they show that there is the second layer weights are becoming sparse in some sense. Have you seen that?
Is it like yeah, I think they talked a little bit about that. I was mainly looking at generalization bound for that paper. I haven't looked really into that particular section where I think they froze the first layer and they just train the second layer and they see what it does.
Yeah, that's one of the things they did, yeah.
Yeah, I was hoping to calculate the margin. That's the one thing that I was hoping to do, is to figure out how to calculate but the margin is a little bit weirdly defined. Namely, they define some kind of because when you calculate margin, you have to first confine things in the ball, otherwise it can be arbitrarily big. So the functional norm they used was some kind of weird variational norm that I still have to figure out how it's a meaningful way to code it in a discrete setting, because again, it's like some kind of measure theoretic nonsense, right? Like you have to take infimum of all the possible measures. So it's not very obvious how you can this thing. So I guess I have to figure out how they did their numerical experiment. But it's in general very difficult. It's not very quantitative, whatever they're doing.
Yeah, but they do have nice plots, right? They do have nice plots.
Yeah, they do. So I guess I'll just try the testing thing, the generalizability. I think maybe I'll use that as a criteria.
I was thinking that maybe there should be like, if you look at their blog, it shows that there is interesting like piecewise linear prediction boundary, right? I don't know if you've, maybe I can send you the picture I'm talking about. Let's see.
Piecewise linear.
Yeah, this was the. Sorry.
According to the experiments that I ran, they do look like it's kind of piecewise linear. It's very choppy.
Yeah, so that's the thing that's very interesting, in my opinion. Different people.
I can show you a few pictures.
So here's the thing I was talking about, this image. If you look at what happens at the end of training, it's super cool. I think.
How come their network is doing much better than mine?
Notice also that the way they choose the data. Oh, I guess it's kind of similar to yours now that I look at it. They have a grid of size 4 by 4. I see. Yeah. I see. Okay. So that's very cool, actually. I never noticed it's a grid. And you see their sample size is extremely small. It's like 3 examples, 4 examples, right? 2 examples.
So maybe if you reduce the sample size, it becomes easier because like at least training wise, it's easier to minimize.
I think the point is not that it's easier. It should be easier because you have less data that you need to interpolate, right? Like if you have your network is trying to memorize the training data. The less data you have, the easier the task is. It's kind of counterintuitive in some sense, but maybe not. In any case, my point is that if you have less data, if you have infinite data, your prediction boundaries are going to be kind of boring because they're just going to be like perfect decision boundaries that kind of separate the grid. Do you know what I mean?
Yeah, that's kind of what I was observing. If you can see a picture.
Yeah, so if you use less data, you would get more exotic boundaries. Your boundaries don't look perfect. They don't look perfect.
Yeah, but this guy's got like 100% accuracy.
Yeah, something looks strange about your decision. Yeah, I think based on this plot, it seems like you're definitely not optimizing over the learning rate.
Optimizing over the learning. Oh, like the learning rate is not doing.
You should pick the learning, like the number one task of training networks is tuning the learning rate, right? That's what most people spend their life doing.
Oh, really?
Yeah, so learning rate is like
actually
the most important hyperparameter.
Oh. I see. Yeah, I basically stole the learning rate from past homeworks, so maybe that's why it's not.
Yeah, so that's a bad idea because the learning rate from the past homeworks was for like for ResNet, the learning rate is around 0.1. So that's kind of, actually the previous homeworks, the learning rates I was using there, I chose it by optimizing over 25 different initial learning rates. So I chose a specific number usually, which I knew to be the correct number. I didn't just guess a number, if that makes sense.
I see. Yeah,
so I think the first thing is that if you tune the learning rate, you would probably get like these perfect decision boundaries, which would be just like a boxed grid type of thing. And then if you use less data, then you would get a more interesting decision boundary similar to what they got. By interesting, I mean that it becomes like non-perfect, right? Perfect learning rate, perfect decision boundaries are less informative than non-perfect ones.